Okay. Hello, welcome back. So, previous lecture we have seen an algorithm, right, for relational design by synthesis, in which each decomposition will be into 3NF schemas, and also that algorithm preserves the functional dependency preservation property, right? But the problem there was that the algorithm can be lossy, that is, some of the information from the original relation may be lost in the decomposition. Now we are moving to the second algorithm for relational database, that is relational decomposition into BCNF with lossless join property. Okay, so here the different schemas after decomposition will be in BCNF, and also those relations together will have the lossless join property. Okay, so now let us move to the algorithm. Input to this algorithm is also a universal relation R and a set of functional dependencies F on the attributes of R. So as an initialization, we are assigning the initial relation or original universal relation as the value of this decomposition. Okay. Now we have to change this universal relation using this algorithm, step 2. The repeating condition for this step 2 is while there is a relation schema Q in D that is not in BCNF. As long as there is one relation in this set, decomposition set D, which is not in BCNF, we have to do this step. What we have to do is choose a relation schema Q in D. You have to select the corresponding schema which is not in BCNF, and we have to perform the following. What we are doing is actually we have to decompose that Q. Okay, Q is actually the relation which is not in BCNF. We have to decompose that. How we are decomposing is that we will find a functional dependency X determined Y in Q that violate BCNF. Okay, so within that Q, the functional dependencies will be there, right? Among those, we have to find a dependency that violate this BCNF. Say that is X determines Y. So we will decompose this Q into 2 based on this dependency. How we are forming two different components for this Q is replace Q in D by two relations schemas. One is Q minus Y, original relation Q minus the right hand side attributes. That will be one schema, and the second one will be X union Y. The dependency, you have to take the LHS and RHS, take the union. That will be the second relation schema. Like this, all those relation schemas which violates BCNF, we have to perform this decomposition. So this is the algorithm. Now we can just rewind this example. We have already seen this example, the Lord's relational schema, right? And we decompose this original relation into a set of BCNF relation schemas. Okay, so this is the original relation R. Okay, property ID, county name, lot number, area, price, tax rates were the attributes, and these together is a key, and the main key or the primary key is property ID, and county name and lot number together act as a candidate key, right? And if we go through different functional dependencies, this functional dependency, that is county name determines tax rate. This violates this BCNF, right? So we have to select that functional dependency, and what we have to do using our algorithm, initial value for D will be the entire relation lots, right? And we have to find a dependency which violates the BCNF, right? So county name determines tax rate is our candidate dependency. What we have to do? We have to decompose the original relation into two. First relation will be all these attributes minus the Y part of our dependency, right? The Y part, X part is county name and Y part is tax rate. That is the dependency county name determines tax rate. So we have to remove tax rate from this original relation. That will be one relation, and the second one X union Y, right? That is county name union tax rate. That will be the second relation schema. So this is how we divided or decomposed our original relation using this algorithm. Okay. And again we have to check for the same thing, whether any schema violate this BCNF condition. If so, we have to repeat the same procedure again and again So applying this procedure, we will get this lots 1, the first relation, that is lots 1 will be again decomposed into lots 1A and lots 1B, because this area determines price is again a dependency which violates this BCNF. Okay, so based on that, we will decompose this lots 1 into 2 different relations, one in which price is removed. Okay, price, that is the y part of the dependency, that is removed. We will get the first relation, then x union y, that is area and price together will form the second component schema. So we have gone through 2 different algorithms, right? First one, decompose our original relations into a set of relational schemas, each of which is in third normal form, and preserves the dependency preservation property, right? And the second algorithm, each and every relational schema, component schema will be in BCNF, and it preserves this lossless join property or non-additive join property, right? Surely we need an algorithm which have these 2 properties, that is both it should be dependency preserving, and also it should have the lossless join property. Now let us move to such an algorithm. Okay, so this is the algorithm for relational database schema design, which preserve both of the property, dependency preservation and lossless join property. Okay, so here also the input will be a universal relation R and a set of functional dependencies F on the attributes of R. So as a first step, from this set of functional dependencies, we have to find the minimal cover G for F. Okay. And second step, for each left hand side x of a functional dependency that appears in G, create a relation schema in D with attributes x union A1 union A2 union etc. AK, where x determines A1, x determines A2 etc. are the only dependencies in G with x as left hand side. Okay. So first step is same as that of our algorithm for that dependency preservation, right? What we are doing here, we will find the minimal cover of the functional dependency set, the minimal set of functional dependency that is denoted by G, and we have to take each dependency from this G and perform this. What we are doing, we will create a new schema in the decomposition set D. Okay. What are the attributes for that relation schema? We are taking x determines something, right? X is the left hand side. Okay. So x union A1 union A2 union etc. AK. What are A's actually? A's are the right hand side of some dependency in which x is the left hand side. Okay. So all those dependencies we have to take, and the corresponding right hand side attributes we have to take the union. Okay, so all these together forms the relation schema in D. Okay, and what is the key for that? X will be made as a key for this relation schema. X is left hand side. Okay, so like this we have to repeat for each and every functional dependency. So lot of tables or lot of schemas will be created after repeating this step, right? Now, if none of the relation schemas in D contains a key of R, then create one more relation schema in D that contains attributes that form a key of R. Okay. Now, after repeating steps 2 for all the functional dependencies, the last thing to be checked is if none of the relation schemas in D contains a key of R. A key will be given for R, right? And our the newly created relation schemas does not contain this key of R. Then we have to create a additional relation schema, one more relation schema in D that contains all the attributes from the key of R. Okay, corresponding to that key of that original relation R, we are creating a new relation schema also. And step 4 is eliminate redundant relations from the resulting set of relations in the relational database schema. So what do you mean by redundant relation? A relation R is redundant if R is a projection of another relation S in the schema. Okay. In other words, we can say the R is subsumed by S. In that case, we can just eliminate R. Now let us go through an example which makes this algorithm clear. Okay, let us take the other example itself, in which let us take the relational schema corresponding to loads 1A. Okay, loads 1A. That is this schema we are taking as the universal relation. Okay, so 4 attributes are there: property ID, county name, lot number and area. Okay, and we have given a set of functional dependencies also. So 3 functional dependencies are there. First one is property ID determines lot number, county name and area. Lot number and county name together determines area and property ID, and area determines county name. These are the functional dependencies. So for simplicity, let us just represent this property ID by P, lot number by L, county by C, area by A. Okay, then let us represent these functional dependencies like this. P determines LCA, lot, county, area, like that. Second one is L and C together, right? Lot and county together. LC determines area and property ID, AP. And third one is area determines county, A determines C. These are the functional dependencies. So coming to the algorithm, first step is finding the minimal cover, right? We have to refer the earlier algorithm to find the minimal cover. And when we apply this minimal cover algorithm, we will get this set of functional dependencies. Okay, P determines L, C, A, LC determines A, P, A determines C. Okay, and if we are going through this different functional dependencies, we can observe that this P determines A can be inferred from other dependencies, like P determines LC is there and LC determines A is there, right? So by transitive rule, we can infer this P determines A. So it is actually redundant. We can remove that dependency. So P determines LC, LC determines AP, and A determines C are the set of functional dependencies in the minimal cover. Okay, so we found the minimal cover, then going to the algorithm. So our first step in algorithm, or the main step in algorithm, is we have to find a dependency X determines Y, right? And we have to create a relation for that. So all this dependency we have to refer each and every one. P determines LC first we have to take into consideration. So corresponding attributes will be PLC. We don't have any other dependency in which P is the left hand side, right? So R1 will be PLC with P as the key. And going to the next relation, that is dependency, that is LC determines AP, right? So we don't have any other relation with LC as the left hand side. So corresponding to this dependency, we have to create a new relation schema in which LCAP will be the attributes and L and C together will form the key. That is the second relation. Okay. And coming to the third dependency, A determines C, we have to create a new schema, relation schema with two attributes A and C, in which A will be the key. So R3 will be like this. So after step 2, we got the design as 3 relation schemas R1, R2 and R3, right, with these attributes. And step 3, we have to check whether our key in the original relation is there in any of these relations. The key in the original relation was property ID P, right? It's already there in one relation. So step 3 is not needed. Now step 4. What was step 4? Eliminate all those relations which are projection of some other relation. So if we go through this 3 different relation schemas, we can see that R1 is actually projection of this R2, right? Like that, this R3 is also a projection of this R2. R3 contains 2 attributes A and C, which is there already in R2. Like that, R1 also contains 3 attributes which is there in R2. So we can see that R1 is subsumed by R2 and R3 is also subsumed by R2. That means R1 and R3 are redundant. We can just eliminate those two relational schemas. Final design will contains only one relational schema R2 with 4 attributes L, C, A and P, in which L and C will be the keys. So this is how we can decompose our original relations into a set of 3 of relation schemas, preserving both properties. Those are lossless join property and dependency preservation property. Thank you.